How big is the universe? People ask it like there's a simple answer. There isn't, because the universe has no wall, no edge, no place where space stops. What we can measure is the part whose light has had time to reach us in 13.8 billion years. And to make sense of that number, you need something to hold it against. So we'll use the only thing we know from the inside, our own galaxy, 100,000 light-years wide, hundreds of billions of stars, so large that our sun has circled it only about 20 times in 4.5 billion years. That's our measuring stick. And by the end, you'll have a real answer to how big is the universe, and you'll actually understand it. Let's climb it together, one honest step at a time. Now get yourself comfortable, hit subscribe. We begin. Go far enough from any city, on a clear night with no moon, and something appears overhead that most people alive today have never actually seen. A faint band of light, pale, uneven, stretching from one horizon to the other, like smoke that refuses to drift. Ancient cultures called it a river, a road, a spill of milk across the sky. Every one of those names describe the same thing, a soft glow with no visible source. And here is the first thing worth understanding carefully, because everything that follows depends on it. You are not looking at the Milky Way, not the way you look at a mountain or a distant coastline, or anything else you have ever seen from outside. You are looking through it, sideways, along the plane of a structure you happen to be standing inside. Picture yourself in the middle of an enormous flat forest at night. Look straight up, and you see open sky between a few branches. Look sideways, along the ground, and the trunks pile up behind each other until they merge into a solid wall of wood. Same forest, different amount of it in your line of sight. That pale band is simply the direction in which our galaxy runs deepest. The disk we live in stretches roughly 100,000 light-years across, and when you look along it, you are staring down a corridor packed with billions of stars, one behind another, most of them thousands of light-years away. Not one of them is bright enough on its own to register in your eye. Together, they smear into a single wash of light. You have seen this exact effect before. Look down at a city from a plane at cruising altitude, and the individual windows, headlights, and street lamps dissolve into one continuous orange stain. Your eye simply cannot separate points of light that close together at that distance. The stain is real. The individual sources are real. Your biology is the thing that fails. For most of human history, nobody knew that. The band was a feature of the sky, not a collection of objects. Then someone pointed a lens at it. In March of 1610, Galileo Galilei published a short pamphlet describing what he had seen through a hand-ground tube of glass, an instrument no more capable than an ordinary pair of binoculars you could buy today. When he turned it on the Milky Way, the glow resolved into a cluster of many separate stars. He wrote that the galaxy was nothing but a mass of innumerable stars grouped together, and with that sentence, a permanent feature of the sky became a collection of individual objects. The wash had components, the band was made of things, but knowing what something is made of tells you almost nothing about its shape. In 1785, William Herschel published the results of counting stars across 683 separate regions of sky, working alongside his sister Caroline. The logic was elegant. Count more stars in one direction, and the system must extend further that way. He assumed every star shone with the same true brightness, and he assumed he could see all the way to the edge. From those counts, he concluded that the sun sat near the center of a flattened, roughly elliptical system, extending about 5 times further along the plane than perpendicular to it. The flattened shape, correct. The sun at the center, completely wrong. And the reason he got it wrong is the same reason this entire subject remains difficult. Imagine standing in thick fog holding a lantern. You can see perhaps 20 meters in every direction, and beyond that, nothing. Turn slowly, all the way around. The fog looks identical everywhere. Naturally, inevitably, you conclude you are standing in the middle of it. The Milky Way is full of interstellar dust, and that dust cut Herschel's view short in every direction equally. He was standing in fog with a lantern, and he drew the only map the fog allowed. We now classify the Milky Way as a barred spiral galaxy, and each part of that description corresponds to something physical. There is the disk, flat, wide, rotating, holding almost all the young stars and nearly all the gas and dust from which new stars form. At its heart sits a central bulge roughly 10,000 light-years across, packed with older stars. Cutting through that bulge runs a straight, elongated bar of stars, and winding outward from the bar are the arms, trailing lanes where gas piles up and star formation runs hot. Our position in that structure matters enormously, and here is why. If you could safely stand on a planet deep inside the central bulge and look up after sunset, you would see something no human being has ever seen. Astronomers estimate the sky there would hold around 1 million stars as bright as Sirius, the brightest star in our own night sky, bright enough that night would not look very different from day. No true darkness, not once in your entire life. No moment of standing under a black sky wondering what is out there, because there would be no black sky to stand under. We live somewhere far quieter than that, but we still cannot see our own home clearly, and astronomers are still arguing about its basic shape. Here is a question that sounds like it should have been settled a century ago. How many spiral arms does our galaxy have? Radio astronomers using very long baseline interferometry, a technique that links telescopes across continents to measure the positions of young, massive star-forming regions with extraordinary precision, published results in 2019 favouring a 4-armed Milky Way. Observations of Cepheid variable stars from the European Space Agency's Gaia mission, of young stars, of open clusters, and of ionized hydrogen regions have all tended to support that picture. Except infrared surveys tell a different story. The Spitzer Space Telescope's GLIMP survey, which mapped the disk in infrared light that penetrates dust far better than visible light does, revealed only 2 major arms. Earlier stellar density work, including observations from the COBE satellite, pointed the same way, that only 2 of the candidate arms are genuinely major structures traced by the bulk of the stars, and a newer possibility sits between them. Analysis of more than 200 MESA sources combined with Gaia data has proposed a multiple arm shape, 2 inner arms that split outward with additional independent arms further out, which would be a relief to some astronomers because cleanly 4-arm spirals are genuinely rare. One survey of nearly 7,000 spiral galaxies found only a few hundred with 4 arms, grand and symmetric or ragged and fragmentary. The evidence has not settled it, and the reason it has not settled cuts deeper than any single instrument. Every other galaxy we study from outside, a complete object held at arm's length. Our own galaxy is the one object in the universe we can never step back from. We are inside the thing we are trying to see. Let's be precise about the size, with the honesty the measurements deserve. The disk runs somewhere around 100,000 light-years in diameter, though different methods give different answers, with one careful measurement of the bright inner disk coming in nearer 87,000 and outer structures extending further still. Take the round figure and make it real. A beam of light leaving one edge of our galaxy tonight would need 100,000 years to reach the other edge. When that beam set out, the last ice age was already underway. That glacial period ran from about 115,000 years ago until roughly 11,700 years ago. Everything after it happened while the beam was still in flight. Agriculture, the first cities, writing, every empire, every war, every person you have ever heard of, all of it during a single crossing of one galaxy at the fastest speed the universe permits. Now the other dimension, the one nobody expects. The star-forming layer of that disk is only about 1,000 light-years thick, 100,000 across, 1,000 deep, a ratio of 100 to 1. Find a compact disk if you still have one in a drawer. A standard CD measures 120 millimeters across and 1 2/10 of a millimeter thick, 100 to 1, almost exactly. That thin, glinting sliver you can bend between two fingers has the same proportions as the structure holding every star you have ever seen. Hold it flat at eye level, and you have our galaxy in your hand. Where on that disk are we? In 2019, the Gravity Collaboration, an international team using the European Southern Observatory's Very Large Telescope in Chile, tracked a single star through its 16-year orbit around the black hole at our galaxy's center and measured our distance from it to within 0.3%. Their figure? 8,178 parsecs, or about 26,600 light-years. 0.3%. Measure out a kilometer of road and be wrong by 3 meters. That is the accuracy they achieved on a distance of 26,000 light-years. Other methods land nearby. A Japanese radio astronomy project called Vera, tracking the positions and motions of stars across our neighborhood, put the figure at 25,800 light-years, with the Sun moving at about 227 kilometers per second. Call it roughly 26,000 light-years, a little over halfway out from the center toward the visible edge. On that compact disk in your hand, we sit about 3 centimeters out from the middle, 1.25 inches. The light arriving from the galactic center tonight left 26,000 years ago. Ice sheets were at or near their greatest extent, covering much of northern North America, northern Europe and Asia. Sea levels sat roughly 125 meters, 410 feet, lower than today. That light has been traveling toward your eye since before anyone planted a seed. We are not parked here. The solar system moves through its orbit at about 230 kilometers per second, 828,000 kilometers per hour, or 514,000 miles per hour. At that speed, an object would circle the Earth's equator in 2 minutes and 54 seconds. In the time it took to read that sentence, you moved further than the distance across most countries, and you felt nothing. No wind, no pressure, no sense of motion at all, because everything around you moves with you. The planet, the air, the chair beneath you, the blood in your arms. Motion you share completely is motion you cannot detect. Now hold that speed in mind and guess how long one lap takes. Roughly 225 to 250 million years. 230 million is the figure most often quoted, though the number is not pinned down. It depends on our exact distance and the shape of the galaxy's rotation. Astronomers call one lap a galactic year. The last time the Sun stood where it stands tonight, the first dinosaurs were only just beginning to appear. Everything that has happened in the story of land animals since, their rise, their reign, the asteroid, the mammals, us, has happened in a single circuit. Complex animal life took hold in the seas around 539 million years ago. That is a little over 2 galactic years. Every animal that has ever lived contained inside 2 laps. And the Sun itself, in the whole 4.5 billion years of its existence, has completed roughly 20 orbits. 20. That is the entire travel history of our star. So how many stars share this disk with us? Current estimates run from 100 billion to 400 billion. Start counting now. 1 star every second, no sleeping, no pausing. Reaching the lower figure would take more than 3,000 years. Reaching the higher figure would take nearly 13,000. The uncertainty alone, the gap between the two numbers, would take about 9,500 years to count off, 1 per second. That is not sloppiness. That is dust. Looking toward the galactic core in visible light is like trying to read the far wall of a room filled with wood smoke. The nearby furniture is clear. Everything past a certain depth simply is not there for you. Most of our own galaxy has never been seen in ordinary light by anyone. We live inside it, and we cannot take an accurate census of it. There is another reason the count stays uncertain, and it changes how you should picture the galaxy entirely. Roughly 3/4 of the stars in the Milky Way are red dwarfs, small, cool, low-mass stars burning their fuel with extraordinary slowness. Not one of them is visible to your unaided eye. Even Proxima Centauri, the closest star to the Sun, is far too dim to see without a telescope. Every star you have ever picked out of the night sky belongs to the bright minority. The true population of our galaxy is invisible to us, and they last. Because fusion runs so slowly in their cores, red dwarfs can burn for tens of billions and even trillions of years, many times the current age of the universe. Put that in proportion. If the sun's entire life were compressed into a single day, a red dwarf's life on the same scale would run for months. Some of the red dwarfs shining above you tonight formed before the sun existed. They will still be burning, quietly, long after the sun has faded to a cooling ember. Which brings us to the oldest residents. The most ancient stars in the Milky Way formed more than 13 billion years ago, near the beginning of everything. One of them, catalogued as HD 140283 and nicknamed the Methuselah star, sits about 200 light-years away in the constellation Libra, close enough to study in detail. Its age has been genuinely difficult to pin down. Early estimates around the year 2000 put it near 16 billion years, older than the universe, which is impossible. Refined measurements brought it to about 14.5 billion, with an uncertainty of roughly 800 million years. A reanalysis in 2021 landed nearer 12 billion. The exact figure remains unsettled. What nobody disputes is that this star was already burning when the universe was young, and it is sitting in our own neighborhood, close enough to photograph. Our galaxy is not merely enormous in space, it is enormous in time. It holds objects that predate the Earth, the Sun, and very nearly the universe's first light. Stand under that pale band again and hold everything at once. A disk 100,000 light-years wide and 1,000 deep, somewhere between 100 and 400 billion suns. A central region so crowded that darkness never falls. Stars older than almost anything that exists. A rotation so vast that the age of the dinosaurs fits inside one lap. And us, 26,000 light-years out, moving at 500,000 miles an hour without feeling a thing. It feels like everything. It feels like the whole of reality, wrapped in a single band of light. Hold on to that feeling for a moment longer. Notice how complete it seems, because we are about to take exactly one step outward, and that feeling will not survive it. The step is not to another galaxy. Not yet. The step is to ask a simpler question, one that sounds almost naive until you follow it properly. How far can anything be seen at all? And the moment you ask it, you run into a phrase that almost everyone uses incorrectly, including sometimes people who should know better. The observable universe and the universe are not the same thing. Those are two different words describing two entirely different objects, and the difference between them is not a technicality. Everything that follows depends on keeping them apart. Here is the doubt you are probably already forming, so let's deal with it first. If astronomers can quote a size for the observable universe, and they can precisely, then surely it has an edge. Surely somewhere out there sits a boundary, a final galaxy, a place where space simply stops. No, nothing in our physics suggests any such place exists. The observable universe is best thought of as a bubble with us at its center, while the universe itself is the whole system of matter and energy, possibly infinite and without spatial edges. The size we can quote is not the size of space, it is the size of a delivery zone. Every piece of information you have ever received about the cosmos arrived carried by light, and light, for all its speed, is not instantaneous. So the sphere around us is defined not by any physical structure, but by a deadline, how far light has managed to travel in the time available. Change the time available, and the sphere changes. The universe does not. Two numbers set that deadline, and both are known with startling precision. The first is the age. Measurements from the European Space Agency's Planck satellite give the universe an age of 13.787 billion years, with an uncertainty of just 20 million years. Take a moment with that. The uncertainty is about 1.5 parts in 1,000. Scaled down to a human life, that would be like knowing a person's exact age, to within about 6 weeks, for the entire history of everything. The second number is the speed of light. Just under 300,000 kilometers per second, about 186,000 miles per second, a fundamental limit built into the structure of space-time. Something moving at that speed would circle the Earth's equator 7.5 times in 1 second. And nothing carrying information can go faster. Not radio, not gravity, not any signal anyone has ever proposed. That is the hard ceiling on what the universe is permitted to tell us. So the answer looks obvious. 13.8 billion years of travel time at 1 light year per year gives a radius of 13.8 billion light years, and a sphere about 27.5 billion light years across. Clean, logical, and wrong. In a static universe, that calculation would be exactly right, but the standard cosmological model gives the observable universe a present-day radius of roughly 46.5 billion light years, a diameter near 93 billion. Look at those two figures side by side. Light has been travelling for under 14 billion years, and yet the region it has crossed is now more than 46 billion light years wide. Nothing broke the speed limit. The question simply contained a hidden trap. Here is what the intuitive calculation forgets. It assumes the distance stayed still while the light crossed it. Picture yourself walking towards someone standing at the far end of an enormous hall. You walk at a fixed pace. You cannot go faster, ever. But the floor beneath you is being stretched continuously along its entire length. Every second, every part of the floor between you and them grows slightly longer. Your speed never changes. The journey gets longer while you are making it. And when you finally arrive, the place you started from is much further behind you than it was when you set out. That is what happened to the ancient light reaching our telescopes tonight. Objects that emitted light 13.8 billion years ago from a distance of around 13.8 billion light years now sit roughly 46 billion light years away. So a single distant galaxy has 3 different distances attached to it: where it was when the light left, how far that light actually travelled, and where the galaxy sits right now, a position we cannot see and will not see for an unimaginably long time. The picture arrives. The subject has moved on. That claim demands evidence, and it has some. On March 15th, 1929, Edwin Hubble published a short paper in the Proceedings of the National Academy of Sciences, working with radial velocities for 46 galaxies, though reliable individual distances for only 24 of them. The pattern he found was blunt. The further away a galaxy sat, the faster it appeared to be receding, and roughly in proportion. Twice as far, twice as fast. Astronomers read that motion in the light itself. Stretch a wave and it grows longer, and for visible light, longer means redder. Expanding space stretches the light crossing it, so the light from distant galaxies arrives shifted toward the red end of the spectrum, and the further it has come, the more stretched it is. Now here is what most people misunderstand about that result. Galaxies are not flying outward from some central point, like debris from a bomb. Think of raisins set through a loaf of dough as it rises in a warm oven. Every raisin drifts away from every other raisin, and the ones furthest apart separate fastest. But no raisin sits at the center, and none of them is doing the moving. The dough between them is what grows, which produces a genuinely strange consequence. Every observer, in every galaxy, everywhere in the universe sees exactly what we see. Everything receding, themselves apparently at the middle of it. Everyone is at the center, which means no one is. Let's be precise about what we mean and state it plainly. Our galaxy, roughly 100,000 light-years across. The observable universe, roughly 93 billion light-years across. The ratio comes to about 930,000 to 1. Try to shrink it into something holdable. Reduce the entire Milky Way, every star, every nebula, every world, to a single grain of sand, 1 millimeter wide. On that scale, the observable universe becomes a sphere nearly a kilometer across, more than half a mile in every direction around one grain of sand. And notice what that image quietly destroys. The grain of sand is not empty. It holds hundreds of billions of suns, ancient stars, a supermassive black hole, and one small blue planet with everyone you have ever loved on it. The comparison delivers the ratio and throws away the contents. That is the honest situation. Human scale analogy genuinely fails here, not because the arithmetic is hard, but because our minds are not equipped to hold a number this size, while also holding what fills it. So use light instead. A beam crossing our galaxy needs 100,000 years. A beam crossing the observable universe has never managed it, not once, not in the entire history of time. Stand on a shoreline and look out to sea. A line cuts across your vision where the water meets the sky, and past that line, you can see nothing at all. But nobody believes the ocean stops there. The water continues past the curve of the earth unbroken, indifferent to your eye height. Walk down the beach, and the line follows you, always the same distance away, always centered on wherever you happen to be standing. The cosmic horizon works the same way. Beyond it, galaxies almost certainly stretch on. The same kinds of galaxies, obeying the same physics, with the same clusters and voids and quiet stars. Their light simply has not had time to arrive, and with each passing year, light from objects a little further out reaches us for the first time. The observable universe slowly deepens, a shoreline that keeps revealing more ocean. Except there is a problem with everything just described, a serious one. Every figure for the size of the observable universe depends on knowing precisely how fast space is expanding. And that number, cosmology's most basic parameter, is currently the deepest unresolved measurement problem in the field. Astronomers quote the expansion rate in kilometers per second per megaparsec. A megaparsec is simply a distance, about 3.26 million light years. So the number tells you how much faster a galaxy recedes for every 3.26 million light years of extra distance. Two ways exist to measure it. Both are excellent. They disagree. The first climbs a ladder. Astronomers measure nearby stars of known brightness, use them to calibrate more distant markers, and step outward rung by rung until they reach galaxies far enough away that expansion dominates. Using 42 nearby Type 1a supernovae calibrated by Cepheid variable stars, the SHOES team led by Adam Rees reported an expansion rate of about 73, roughly 73 kilometers per second, or 45 miles per second per megaparsec. The second method never uses a ladder at all. It reads the faint microwave glow left over from the young universe, then works forward using the standard cosmological model to predict what today's rate must be. The Planck satellite's analysis gives 67.4 with an uncertainty of half a point, 73 against 67.4, both with small error bars, both refusing to move. The obvious explanation was a flaw in the ladder, and the prime suspect was crowding. Cepheid variable stars, the rungs of that ladder, sit inside crowded, dusty galaxies. If nearby stars blended into them in Hubble Space Telescope images, they would look brighter than they really are, and every distance beyond would be skewed. The James Webb Space Telescope, with far sharper vision, was pointed at the same stars to test exactly this. Rees and colleagues published the result in 2024. Unrecognized crowding is rejected as the explanation for the Hubble tension at 8 sigma confidence. That phrase deserves translating. In physics, 5 sigma is the gold standard for declaring a discovery, corresponding to roughly a 1 in 3.5 million chance that the result is a statistical fluke. 8 sigma sits far past that threshold. The suspected flaw was not the flaw. The disagreement survived. But that is not the whole story, and honesty requires the other side. Wendy Friedman's Carnegie Chicago team measures distances using a different marker entirely, the tip of the red giant branch. Old red giant stars brighten as they age until a sudden change in their cores caps their luminosity, producing a sharp, reliable ceiling in brightness that works as a standard yardstick. These stars sit in quiet, galactic halos away from the dust and crowding that complicate Cepheids. Using James Webb data, Friedman and colleagues reported a value near 68.8 in 2025, and around 70 when combining that method with Cepheids and a third marker along the same ladder, a middle value. Close enough to Planck to raise the possibility that the whole tension is a calibration problem. The SHOES team, working with a larger sample of the same kind of stars, gets 72 to 73 instead, and argues that sample selection explains the gap. As it stands, the disagreement between the local measurement and the early universe prediction runs at roughly 5.8 sigma, past the discovery threshold, well past coincidence. Nobody has resolved this. Some researchers expect a systematic error will eventually surface. Others suspect something is genuinely missing from our model of the early universe. An extra ingredient, a different behavior of dark energy, some physics we have not written down yet. Both possibilities remain live. More independent distance markers, more James Webb calibrations, and eventually gravitational wave measurements that bypass the ladder entirely may settle it. And notice what this means for the number we were just handed. The 93 billion light-years has a genuine, unresolved uncertainty built into its foundation. One last thing about this sphere, and it reframes everything inside it. Looking outward is looking backward. Always. There is no other option. The sunlight on your skin is 8 minutes and 19 seconds old. The light from the nearest star beyond the sun left just over 4 years ago. Look far enough, and you are seeing galaxies as they existed before the Earth had formed. So the observable universe is not a photograph of how things are. Nothing in it is current. The nearby parts show you the recent past, the middle distance shows you a much older past, and the outermost regions show you the universe in its infancy. Think of exposed rock in a cliff face, layer stacked on layer, each one a different age. Distance is depth, and depth is time. What we call the observable universe is not a snapshot at all. It is a 4-dimensional archive, and every direction you look is a core sample through cosmic history. You cannot see the universe as it is. You can only see what it has already finished being. So we have the outer boundary of what light permits us to know, 930,000 times the width of our galaxy, with a genuine argument still running about the number itself. But before going further outward, we have to go back, because there is a problem with the figure we started from. That 100,000 light-years is not the size of our galaxy. It is the size of the part that glows, and what surrounds it emits no light at all. Before we reach the part that emits nothing, we have to pass through the part that does, because even the glowing portion is not what it appears. That flat disk is not a single object, not one population, not one age, not one chemistry. Layer sits on layer, each with its own history, each moving differently, each holding stars born in a different era of the galaxy. Think of a city seen from above at night, one glowing sprawl. But walk into it, and you find the new districts, the older quarters, and the ancient core beneath the streets, all occupying the same footprint, all built at different times. Our galaxy is layered exactly like that, and the layers do not mix. The innermost layer, the one holding the spiral arms, astronomers call the thin disk. Here sit the dense clouds of molecular gas, cold, dark, and heavy enough to collapse under their own weight into new suns. This layer is the only part of our galaxy still actively manufacturing stars, and it produces some extraordinary ones. Hot blue stars classified O and B, meaning simply the hottest and most massive categories on the stellar scale. They shine millions of times brighter than the sun, and exhaust their fuel in only a few million years. Consider what that means. Our sun will last roughly 10 billion years. Scale that down to a human life of 80 years, and one of those blue giants would live about 2 weeks. They burn like a bonfire soaked in fuel. Spectacular, brief, and then gone in a supernova. Because they die so fast, they never travel far from where they formed. Wherever you see a cluster of them, you are looking at a region of active star birth right now, a place where the galaxy is still working. They also form in company. Open clusters, loose groups typically holding hundreds to a few thousand sibling stars, born from the same cloud, drifting apart over time like a graduating class scattering into the world. You do not need a telescope to find one of these places. Look at the sword hanging below Orion's belt on a winter night, and the faint smudge visible to the unaided eye is the Orion Nebula, roughly 1,344 light-years away, and the closest known region of ongoing massive star formation to our solar system. The nebula itself measures about 24 light-years across, a cloud so vast that light, which crosses from the sun to the Earth in 8 minutes, needs 24 years to cross it. Now place yourself inside that scene. From a safe vantage point at its edge, you would see enormous curtains of hydrogen gas glowing pink and green, lit from within by a handful of ferociously hot young stars at the center. Ultraviolet radiation from those stars strips electrons from the hydrogen around them, and when the electrons recombine, the gas glows. The nebula does not shine by reflection. The cloud itself has been switched on. Astronomers have identified some 700 young stars in the central region alone, along with more than 150 protoplanetary disks, embryonic solar systems that will eventually form planets. 4.6 billion years ago, our own sun almost certainly formed in a cloud very much like this one anonymous star among hundreds, in a nursery that has long since dispersed. Every sibling star born alongside it is still out there somewhere in the disk. We simply cannot tell which ones they are, but that active layer sits inside a second, thicker one. The thick disk holds roughly 10 to 20% of the mass in the thin disk, and its stars are older on average, with lower metal content, on orbits carrying them well above and below the plane. Two things there need explaining. In astronomy, metals means everything heavier than hydrogen and helium, carbon, oxygen, iron, all of it. Those elements did not exist at the beginning. Stars manufactured them and scattered them outward when they died, so the metal content of a star records how enriched the galaxy was on the day it formed, and we can read that record directly. Split a star's light into a spectrum, and dark lines appear at precise positions, each one the fingerprint of a specific element absorbing its own wavelength. A barcode printed by physics, readable across thousands of light years. The thick disk came together relatively early, over a relatively short period, with an average metal content far below the sun's. So the stars swinging above and below our plane are not merely older. Their chemistry preserves the composition of a younger, poorer galaxy, one that had not yet built the raw material for rocky planets. Beyond both disks lies something with a completely different shape, the stellar halo, roughly spherical, containing only about 1% of the galaxy's total stellar mass, dominated by old, metal-poor stars, most of them probably older than 12 billion years, one star in 100. And yet those few are the most informative stars we have, because they were among the first objects our galaxy ever made. Astronomers call them Population 2, ancient, red, and formed from gas that was still close to pure hydrogen and helium. Stars built before the universe had much else to build with. Scattered through that halo sit the most spectacular structures our galaxy contains. About 150 globular clusters are known in our galaxy, nearly symmetrical spheres typically holding hundreds of thousands of stars, with ages generally estimated between 11 and 13 billion years. The density inside them defies intuition. At the center of a globular cluster, stars can reach a density between 100 and 1,000 per cubic parsec. Near our Sun, the figure is about 14/100ths of a star per cubic parsec. Imagine seeing it firsthand. If Earth orbited one of the inner stars of a globular cluster, the night sky would be transformed. The nearest stars would sit light months away rather than light years, appearing as points of light far brighter than anything in our sky, and the band of the Milky Way would probably be lost behind the bright haze of cluster starlight. Thousands of brilliant stars packed into a few light years in every direction you turned. And here is the strange thing about these objects. Many of them are not native. The Sagittarius dwarf galaxy, discovered in 1994, is being torn apart by our galaxy right now, leaving a stream of its stars wrapped across the sky. When a small galaxy gets shredded like that, its dense core can survive the process. Several of the globular clusters orbiting us today are almost certainly the stripped hearts of galaxies the Milky Way has already eaten. Trophies, still in orbit. Those ancient clusters once did something remarkable. They nearly overturned the Big Bang. Because their ages can be estimated from stellar physics alone, without any reference to the expansion of space, they set an independent floor on how old the universe must be. The universe cannot be younger than the things inside it. Then came the problem. For about 30 years, globular cluster ages sat around 15 billion years. Meanwhile, the higher measured values of the expansion rate implied a universe younger than the clusters themselves, and during the 1980s this gave rise to serious speculation that the Big Bang model was fundamentally wrong. Stars older than time, that is not a small inconsistency. The resolution arrived between 1995 and 2003, and it came from three directions: a large Hubble Space Telescope program measuring the expansion rate, parallax measurements from the Hipparcos spacecraft that revised globular cluster distances upward by 5 to 10%, making their stars intrinsically brighter and therefore younger, around 12 to 13 billion years, and the discovery that the expansion has been accelerating, which makes the universe older for any given expansion rate. The clusters were not wrong. Our measurement of everything around them was. Hold that thought, because the same problem, the same disagreement over the expansion rate, is still with us today, and its shadow reaches everything we are about to measure. At the heart of all these layers sits the object everything else orbits. Sagittarius A star, a black hole of about 4.1 million solar masses measured by tracking a single star called S2 through a 16-year orbit around an unseen mass. 4 million suns, and the region it occupies is astonishingly small. The event horizon spans roughly 23.5 million kilometers, about 14.5 million miles. Set it where our Sun is, and the entire thing would fit comfortably inside the orbit of Mercury. On May 12th, 2022, scientists released the first direct visual evidence of Sagittarius A star. The Event Horizon Telescope captured it by linking 8 existing radio observatories across the planet into a single Earth-sized virtual telescope. The image took 5 years to produce, and the difficulty was not distance, it was speed. Gas orbiting the far larger black hole in Messier 87 takes days to weeks to complete a circuit. Around Sagittarius A star, the innermost material completes an orbit in roughly 30 minutes. The subject would not hold still. Photographing it was like photographing a spinning propeller with a shutter left open for hours. And yet, for all its mass, our black hole is quiet. One astrophysicist described it plainly. It has a very low mass supply, essentially starved. Consider what would change if that stopped being true. Some galaxies host black holes actively feeding on enormous quantities of gas, and the infalling material heats and blazes as a quasar, outshining every star in the galaxy combined. Our center almost certainly went through active phases in the past. If it began feeding at that scale again, the galactic core would flood with hard radiation, and the sky 26,000 light-years away, here, would carry a new and permanent glare. That is not happening. But dormant is not the same as dead. And now the layer that changes the size of everything. Beyond the stars, beyond the globular clusters, beyond the visible halo, Our galaxy is thought to sit inside an enormous cloud of dark matter, material that emits no light, absorbs none, and reflects none. We detect it by one property alone: gravity. Recent simulations suggest that this dark region, containing some visible stars as well, may extend to a diameter approaching 2 million light-years. Set that against the 100,000 light-years of glowing disk we started with. The part of our galaxy you can see may be a small, bright core inside something vastly larger. But here is the problem. The evidence for that halo comes from how fast stars orbit at large distances. Too fast for the visible mass, and something unseen must be holding them. Except in 2023, Yongjun Jiao and colleagues used the third data release from the European Space Agency's Gaia mission to build a new rotation curve, and found it dropping sharply. A decline of about 30 kilometers per second, roughly 19 miles per second, between distances of about 64,000 and 86,000 light-years from the center. They identified a Keplerian decline, the fall-off you expect when almost all the mass sits inside, and rejected a flat rotation curve at 3 sigma. Their estimate for the total mass of the Milky Way came out near 206 billion suns, 3 to 5 times below pre-Gaia estimates. Similar declines at large radii were reported by Wu and colleagues in 2024. That would be a dramatically lighter galaxy than anyone expected. Other researchers are not convinced. No consensus has been reached about the outer rotation curve. Some analyses find the sharp decline, others find an almost flat profile out to comparable distances. The discrepancies may come from the non-stationarity of stellar systems, poor tracer selection, asymmetries, and inaccurate distances, and the Jeans equation, with its assumptions of stationarity and symmetry, has come under close examination. Plainly stated, those methods assume the galaxy is settled and symmetric. Our galaxy is warped, still being disturbed, and demonstrably not at rest. If the assumption fails, the mass estimate fails with it. And the stakes are clear enough. If the decline is real, the amount of dark matter required is significantly smaller than the standard cosmological model predicts for a spiral galaxy like ours. Nobody has settled this. Both readings remain live, and the answer will come from better tracers further out. One thing, though, is not in dispute. Our galaxy has been growing by consumption. The last major merger was with a system known as Gaia Sausage Enceladus, about 8 to 10 billion years ago, and roughly half the stars in the galactic halo descend from it. Around 100 stellar streams have now been identified in Gaia data, thin ribbons of stars strung along the orbits of the galaxies they used to belong to. The wreckage is still arranged in the shape of the collision, and Sagittarius is still going. It contains only a few tens of millions of stars, making it 10,000 times less massive than the Milky Way. And as our gravity pulled it in, it began smashing through our disk, at least 3 times, 5 or 6 billion years ago, 2 billion years ago, and 1 billion years ago. A galaxy has already passed through the plane we live in, more than once. So the figure we began with was never the whole object. Our galaxy is larger than its light, heavier than its stars built from the remains of others, and the meal is not finished. But even at its most generous estimate, this entire structure is only one member of something larger, and the nearest of its neighbours is close enough to see with your own eyes. On a clear autumn night, away from streetlights, look toward the constellation Andromeda, and you will find something most people walk past their entire lives. A faint oval smudge, small, grey, easy to mistake for a flaw in your vision or a wisp of cloud. Hold your gaze on it and understand what you're actually looking at. Not a star, not a nebula, an entire galaxy, roughly 2.5 million light-years away, the nearest large galaxy to our own, and one of the 2 giants that dominate everything around us. The photons entering your eye at that moment left their stars 2.5 million years ago. When that light departed, the Pleistocene, the long series of ice ages, was only just beginning. Homo habilis, one of the earliest members of our own genus, walked in East Africa. Our species did not exist and would not exist for millions of years. That smudge is usually described as the most distant object the unaided human eye can see, though under exceptionally dark skies, some observers report catching the Triangulum Galaxy, which lies further still. Either way, the principle holds. Standing on a hillside with no equipment at all, you can look directly at something outside our galaxy. Our galaxy has never been alone. It belongs to a gravitationally bound family. Astronomers call it the local group, and its members are spread through a volume nearly 10 million light-years across, centered somewhere between the Milky Way and Andromeda. The word bound matters more than it sounds. Everywhere else, space is expanding and carrying galaxies apart. Inside a bound group, gravity has already won. These galaxies are not drifting with the expansion. They are held, orbiting each other, permanently linked. Picture a river carrying leaves steadily downstream, and one small eddy near the bank where a handful of leaves circle each other, going nowhere. The river keeps moving. The eddy stays. We live in the eddy. 3 large galaxies dominate the group. Andromeda, the biggest, our Milky Way, second, and the Triangulum Galaxy, the smallest of the 3. Everything else is dwarf galaxies, most of them orbiting one giant or the other. The exact count remains unknown, because our own galaxy blocks part of the view. 134 members are currently known within a megaparsec of the center, most of them dwarfs. We cannot take a complete census of the family we live in, but the deeper problem is that for most of human history, nobody knew the family existed at all. On Monday, April 26, 1920, at 8:15 in the evening, Harlow Shapley climbed onto the stage of the Baird Auditorium at the Smithsonian Museum of Natural History in Washington, D.C. Facing him was Heber Curtis. The subject was the nature of the so-called spiral nebulae and the size of the universe. Each man got 40 minutes. Shapley believed the spiral nebulae were nearby gas clouds, and the universe was composed of a single large galaxy. Curtis argued the universe contained many galaxies like our own. Here is what makes this debate so remarkable. Both men were looking at the same faint smudge in Andromeda. One saw a small cloud inside our galaxy. The other saw an entire separate galaxy, unimaginably far away. Shapley's objection was straightforward. If Andromeda really was a separate system like the Milky Way, then to appear that small, it would have to be millions of light-years away, and that seemed absurd because the universe was nowhere near so large. He was not being foolish. He was applying the best knowledge available. The debate could not be settled that night, and everyone in the room knew why. Nobody could measure the distance. Without a distance, both interpretations survived, and the size of the universe remained a matter of opinion. What they needed was a ruler. The ruler already existed. It had been published 8 years earlier by someone who was not invited to the debate. Henrietta Swan Leavitt, working at Harvard College Observatory, published in 1912 a relationship between the period and the luminosity of 25 variable stars in the small Magellanic Cloud. Those stars are Cephids, stars that pulse, brightening and dimming on a strict schedule. Leavitt found that the brighter the star, the slower it blinked. Think about what that gives you. Imagine a street at night, lined with light bulbs of unknown wattage. You cannot tell whether a bulb looks dim because it is weak or because it is far away. But now, suppose every bulb flashes, and the flash rate tells you exactly how powerful it truly is. Compare its true power to how bright it looks, and the distance falls straight out. Cephids became the first known standard candles for measuring distances beyond our galaxy, and they remain the gold standard for that task today. Leavitt died in 1921 and did not live to see the impact of her work. She had handed astronomy a measuring tape long enough to reach out of the Milky Way. Someone still had to use it. In late 1923, Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory, at that time the largest telescope in the world, to photograph the Andromeda Nebula. On the 6th of October, he identified a star that had changed brightness compared with earlier plates. A Cephid. Now Leavitt's law could be applied. Over the following weeks, Hubble calculated a distance to Andromeda of about 930,000 light-years, less than half the true value, but more than 3 times larger than Shapley's entire universe. The finding leaked to the New York Times in November of 1924, and Hubble's formal report was read aloud at a joint meeting of the American Astronomical Society on January 1st, 1925. Curtis was right, and consider what actually happened in that moment. In a single measurement, the known universe expanded by orders of magnitude. Every fuzzy spiral in every catalogue stopped being a cloud and became a galaxy, an entire system of hundreds of billions of stars, unreachably far away. Reality did not change that night, only our estimate of it. Shapley, presented with the evidence, eventually abandoned the position he had defended and adopted the one he had opposed. That is what the process looks like when it works. Our neighbour is not a lesser version of us. Andromeda holds its own supermassive black hole at its centre, its own retinue of satellite galaxies, and its own vast halo of dark matter. 2 comparable giants, each with a private family of dwarfs, facing each other across 2.5 million light-years, and moving. Andromeda and the Milky Way are approaching each other at roughly 110 kilometers per second, about 400,000 kilometers per hour, or 250,000 miles per hour, fast enough to cross from London to New York in under a minute, which produced one of the most repeated claims in all of astronomy, that the 2 galaxies are doomed to collide in about 4 to 5 billion years, except that claim no longer holds. In June of 2025, a team led by Till Sawala at the University of Helsinki published a study in Nature Astronomy, using the most accurate observations available from the Gaia and Hubble space telescopes. They considered 22 different variables and ran 100,000 simulations projecting 10 billion years into the future. The reason nobody had done this properly before comes down to one measurement. Astronomers can measure how fast Andromeda approaches us with real precision, because motion straight toward us stretches or compresses its light. Sideways motion is far harder. Judging whether Andromeda drifts slightly left or right is like standing at one end of a stadium and trying to decide whether a person at the far end is walking directly toward you or a few degrees off, except the stadium is 2.5 million light-years long. Small errors in that sideways drift change everything. Sawala's result, approximately a 50-50 chance of the 2 galaxies colliding within the next 10 billion years, and only a 2% probability of a collision in the next 5 billion years, contrary to the previous belief that the demise of the Milky Way within that time frame was a certainty. 2 other galaxies turned out to matter enormously. Including Triangulum increases the merger probability, while the Large Magellanic Cloud's orbit runs perpendicular to the Milky Way Andromeda orbit and makes the merger less probable. As Sawala put it, the Large Magellanic Cloud pulls the Milky Way off the orbital plane and away from Andromeda, not saving us from the merger, but making it a bit less likely. A satellite galaxy, 1/10 our mass, may be steering us away from the largest collision in our future. But that is not the end of it. A more recent analysis revisited the same framework using the latest and most precise Gaia-based motions for Andromeda and Triangulum, corrected for systematic offsets in the astrometry. In their preferred model, the merger probability rises to 90%, with a median merger time of about 6.5 billion years, broadly restoring the classical picture. Their sensitivity analysis found the outcome depends strongly on the adopted sideways motion of Andromeda, so the entire fate of our galaxy currently hangs on how well one number is measured, 50-50 or 90%. Nobody can yet say which, and the honest answer is that better astrometry, more years of Gaia-quality data on Andromeda's drift, will decide it. The fate of the Milky Way remains an open question. Suppose it does. What would that actually look like? Not an impact, not a crash in any sense you have ever witnessed. Here is the crucial fact. Stars almost never physically collide during a galaxy merger. The distances between stars are so enormous compared to the stars themselves that 2 galaxies can pass through each other with virtually no direct hits. Think of 2 vast swarms of gnats drifting through one another across a stadium. The swarms interpenetrate, and almost nothing touches. Gravity does all the work. Tidal forces would drag long streams of stars out into intergalactic space. The gas clouds, which do collide, would slam together and trigger enormous bursts of new star formation. Gas driven to the center of the merger remnant can feed a central black hole, emitting an enormous amount of radiation before falling in. The two galaxies would pass, separate, fall back, and pass again, over hundreds of millions of years, until the spiral structure of both was gone, and what remained was a single elliptical galaxy, a featureless swarm of old stars. Some astronomers have nicknamed the result Milky Way. Imagine standing on Earth's surface midway through that process. The Sun would almost certainly survive, simply relocated onto a different orbit. But the sky above you would be unrecognizable. No calm band of light overhead, but two enormous distorted spirals filling the darkness, bridged by glowing lanes of torn gas, with brilliant new blue stars igniting along the collision fronts. No sound, no impact, just a slow, silent restructuring, lasting longer than complex life has existed on Earth. Long before any of that, our galaxy has a closer appointment. The Large Magellanic Cloud sits about 163,000 light-years away, with the Small Magellanic Cloud further out at roughly 200,000. From the southern hemisphere, both are visible with unaided vision as patchy wisps of light. They are already being torn apart. The Milky Way's gravity rips a stream of gas from both called the Magellanic Stream. That gas stretches for at least 180 degrees across the sky, halfway around the entire celestial sphere, a wound visible from horizon to horizon if your eyes worked in radio wavelengths. And the same study that lowered the odds of the Andromeda merger raised the odds of something else. The Large Magellanic Cloud's influence increases the likelihood that the Milky Way will cannibalize this satellite galaxy within the next 2 billion years. Our galaxy will very probably eat its brightest companion long before it ever meets Andromeda. One more layer, and it changes how you picture our position. The Milky Way lies in a thin plane called the local sheet, part of a wall bounding an enormous empty region known as the local void. Brent Tully has argued that our local sheet is being pushed away from that void at around 260 kilometers per second, roughly 160 miles per second. Altogether, the motions of the Milky Way, Andromeda and their neighbors deviate from the overall expansion of the universe by more than 600 kilometers per second, about 1.3 million miles per hour, and roughly half of that comes from a pull by the massive nearby Virgo cluster, combined with our participation in the expansion of the local void as it empties. We are not simply falling toward Andromeda, we are being pushed from behind by nothing at all, by a region so empty that its emptiness has a measurable effect on where we go. So we have taken one step outward, and the numbers have moved. 10 million light-years across, holding well over 100 known galaxies, two giants circling each other with an uncertain future. One satellite about to be consumed. 100 times the width of the galaxy we began with. Now hold that against the 93 billion light-years we can see. 10 million light-years is about 1/9,000th of the observable universe. Compress the entire visible cosmos to the length of a football pitch, and this entire family, everything we have just walked through, everything reachable, everything bound to us, would occupy a single centimeter of the halfway line. We did not step outward far enough to matter, and the reason is that the local group is not a freestanding structure at all. Something far larger has been quietly steering it the entire time, and we have already felt its pull in these numbers, without naming it. The thing steering us has a name, Virgo. Our entire local group, both giants, every dwarf, everything bound to us, is falling toward a cluster of galaxies sitting in the direction of the constellation Virgo, and has been for billions of years. That cluster anchors a much larger structure, the Virgo supercluster, thought to be about 110 million light-years across, containing at least 100 galaxy groups and clusters. Our family of 100-odd galaxies is one of those groups. a single household in a city we had not yet noticed we lived in. At the heart of it sits the Virgo cluster itself, lying roughly 52 to 55 million light-years away, home to over 150 major spiral and elliptical galaxies and more than 2,000 smaller ones. Think about what that means physically. Our local group spreads its 100-plus galaxies across 10 million light-years of nearly empty space. Virgo packs more than 1,000 into a fraction of that volume. We live in the countryside, that is the city. One galaxy dominates it, and by any standard our own is a modest thing beside it. Messier 87, a supergiant elliptical galaxy containing several trillion stars, one of the largest and most massive galaxies in the local universe, with about 15,000 globular clusters compared with the 150 to 200 orbiting the Milky Way. 100 times as many ancient star swarms as we possess, most of them almost certainly stolen. The surviving cores of galaxies M87 has already consumed. Its bright inner region spans about 120,000 light-years, but deep, long exposure photographs reveal that its outer parts extend across more than half a degree of sky, larger than the full moon, corresponding to an extension of over 1 million light-years. Not a disk, not a spiral, a vast, featureless, yellowing swarm of old stars, 10 times the reach of everything we call home. And at its center sits something that changed astronomy. The black hole in M87 holds 6.5 billion times the mass of the Sun and measures 38 billion kilometers, 24 billion miles, across. That number needs translating because it is meaningless on its own. Light from our Sun takes about 4 hours to reach the orbit of Neptune. M87's event horizon is about 4 times as large as Neptune's orbit, roughly 1.5 light days across. Picture the entire solar system. The Sun, all 8 planets, the whole retinue of ice and rock out past Neptune. Drop all of it into that black hole's horizon, and it would sit near the middle, with room to spare in every direction. The Sun, the planets, and a good portion of the rocks and dwarf planets beyond Neptune could all fit inside. Over 1,000 times more massive than the black hole at the heart of our own galaxy. And unlike ours, this one is not asleep. On the 10th of April, 2019, the Event Horizon Telescope collaboration unveiled the first direct visual evidence of a supermassive black hole and its shadow in 6 papers published simultaneously. The instrument was not a telescope in any ordinary sense. 8 ground-based radio observatories, spread across the planet and linked into a single Earth-sized virtual telescope, dishes in Hawaii and Chile and Spain at the South Pole, all recording the same faint signal at the same moment, their data stitched together afterwards into one image. You have to appreciate the absurdity of the target. 55 million light-years away, and they were resolving a feature the size of a solar system. What appeared was a ring, an asymmetric ring of light wrapped around a circle of pure darkness. The ring appears brighter on one side because the black hole is rotating, so the material turning toward Earth has its emission boosted. As Shep Doeleman of the Harvard-Smithsonian Center for Astrophysics put it, in a paradox of nature, black holes, which do not allow light to escape, are some of the brightest objects in the universe. Nothing escapes from inside, but gas falling toward the edge, whipped to near light speed, blazes. The energy has to go somewhere, and in M87's case, some of it comes out as a beam. A jet of energetic plasma originates at the core and extends at least 4,900 light-years, traveling at relativistic speed, near the speed of light. 5,000 light-years is a fifth of the distance from here to our own galactic center, punched out in a single straight line of glowing plasma. Imagine watching this from a safe distance outside the galaxy. You would see a smooth yellow-white sphere of ancient stars, and lancing out of its exact center, a narrow blue-white searchlight beam, perfectly straight, extending far beyond the visible edge of the galaxy into intergalactic space. That beam has been firing more or less for millions of years, but the black hole is not the most dangerous thing about a cluster. The space between the galaxies is. The Virgo cluster is filled with an extremely hot, thin plasma called the intra-cluster medium, reaching temperatures of tens of millions of degrees and containing more total mass than all of the cluster's visible galaxies combined. More mass in the gaps than in everything you can see. And that gas does something brutal. When a galaxy falls into the cluster and plows through the intracluster medium, the gas acts like a headwind, stripping away the galaxy's own cold gas supply, a process called RAM pressure stripping, which can shut down a galaxy's ability to form new stars. You have felt the underlying physics. Stand still outdoors on a calm day, and the air does nothing. Put your hand out of a car window at speed, and the same still air becomes a force that pushes your arm back. The faster the galaxy moves relative to the hot gas, and the denser that gas is, the stronger the stripping, and it works on a timescale of a few tens of millions of years, far faster than gravitational interactions. The removal of gas leads to what astronomers call environmental quenching of star formation. Here is what that means for a galaxy. Stars need cold gas to form. Strip the cold gas, and the galaxy keeps the stars it already has, but can never make another one. Its blue stars burn out within millions of years, its red ones linger for billions, and the whole system slowly fades to a uniform reddish glow. Not destroyed, sterilized. The Milky Way sits well outside that environment, out in the quiet outskirts, still forming stars, still holding its gas. Consider what would have happened if we had not. Suppose our galaxy had formed a few tens of millions of light years closer in and fallen through the Virgo core early in cosmic history. The hot intracluster wind would have stripped away our reservoir of cold gas. Star formation would have wound down billions of years ago. The heavy elements needed to build rocky worlds would have been locked into a dwindling population of aging stars. The Sun formed 4.5 billion years ago from exactly that kind of cold, dense cloud. In a stripped galaxy, that cloud would not have existed. We are not simply lucky to live in a galaxy. We are lucky to live in one on the outskirts. For decades, astronomers defined superclusters roughly, by eye, by where galaxies looked crowded. Then a team led by Brent Tully at the University of Hawaii tried something fundamentally different. Instead of asking where galaxies are, they asked where galaxies are going. Every galaxy's motion has two parts. One comes from the expansion of space, which is predictable. Whatever remains after subtracting it is called the peculiar velocity, the part caused by gravity alone. Tully's team used a catalogue of peculiar velocities, line-of-sight departures from cosmic expansion caused by gravitational perturbation, to map the distribution of matter. In total, they had distance measurements for more than 8,000 galaxies. The logic is beautiful, and Tully explained it with an image anyone can hold. Within the volume, motions are directed inwards as water streams follow descending paths toward a valley. Stand in a landscape in the rain. You cannot see the shape of the land in the dark, but watch which way the water runs, and the terrain reveals itself. Every drop is telling you where downhill is. Galaxies do exactly that. Their peculiar motions run down gravitational slopes toward whatever mass sits at the bottom. Map enough of them, and you have mapped the invisible landscape, including its watershed boundary, the ridge beyond which the water flows somewhere else entirely. The result, published as the cover story of Nature on the 4th of September 2014, a supercluster 500 million light-years in diameter, containing the mass of 100 quadrillion suns in 100,000 galaxies. They named it Lania Kea, immense heaven in Hawaiian, the name honouring Polynesian navigators who used knowledge of the sky to cross the Pacific, and the Milky Way resides in the outskirts of it. Set that against where we started. 500 million light-years is roughly 5,000 times the width of our galaxy. Compress the Milky Way to the size of a dinner plate, and Lania Kea becomes a structure a mile across. Here is the first complication, and it is permanent. Unlike the local group, Lania Kea is not gravitationally bound. Individual groups and clusters are bound to themselves, but they are not bound together to one another, and instead recede away from each other as dark energy continues to dominate the cosmic expansion. So this vast structure, our home supercluster, the thing that gives our galaxy its address, is temporary. Dark energy will eventually pull it apart. We belong to something that is already dissolving. And here is the second complication. In 2024, the same Cosmic Flows team published new work in Nature Astronomy using the motions of 56,000 galaxies and found a 60% probability that we are part of an even grander structure, potentially 10 times larger in volume, centered on the Shapley concentration. In that analysis, Laniakea is not cleanly separated from the Shapley attractor at all. If confirmed, our home supercluster becomes a sub-basin of something far bigger, exactly as the Virgo supercluster turned out to be a piece of Laniakea. A separate study using the same Cosmic Flows 4 data confirmed the shape, size, and attractor coordinates of Laniakea, so the structure itself is not in doubt. What remains unsettled is whether it is a watershed in its own right or the upper slope of a much larger valley. Co-author Ehsan Korkci put the limitation plainly. Our cosmic surveys may not yet be large enough to map the full extent of these immense basins. We cannot see far enough to know how big the thing we are falling into really is. At the bottom of Laniakea's valley lies a region astronomers have argued about for nearly 40 years. The Great Attractor, a central overdensity roughly 150 to 250 million light-years away, drawing the local group toward it at a peculiar velocity of about 600 kilometers per second relative to the cosmic microwave background, roughly 370 miles per second. And for decades, nobody could look at it properly because of an unlucky accident of geometry. The zone of avoidance, about 20% of the optical sky, hides important structures behind our own galaxy's dust. The Great Attractor sits almost exactly behind it. Infrared, radio, and X-ray surveys eventually pierced that curtain, revealing key players like Able 3627, the Norma cluster, shown to be the nearest massive rich cluster in the local universe, comparable to the well-studied Coma cluster. Were it not for the obscuration by the Milky Way, the prominence of Norma would have been apparent a century ago, and it might have been the best-studied cluster in the local universe, one of the most important structures in our region of space, sitting in plain view behind a wall of our own dust. Beyond the Great Attractor lies the Shapley concentration, roughly 650 million light-years away, in approximately the same direction, the most massive structure within 1 billion light-years of the Milky Way. Current estimates suggest it may account for 30 to 50% or more of the local group's motion. The motion toward the Great Attractor is significant, but shows no sign of galaxies falling in from the far side, suggesting the flow there is part of a larger flow, caused by some more massive attractive center. We are not falling toward one thing, we are falling through a hierarchy of pulls, each one nested inside a larger one. Then, in 2017, came something nobody had mapped before. Yehuda Hoffman, Daniel Pomered, Brent Tully and Helen Courtois published The Dipole Repeller in Nature Astronomy on the 30th of January, 2017, a vast, underdense region operating on our motion from the opposite direction to the Great Attractor. Emptiness cannot push anything. So what is actually happening? Gravity from a region only matters relative to everywhere else. Stand in the middle of a room with a crowd of people pressed against one wall and nobody against the other, and you feel a net pull toward the crowd. Not because the empty wall repels you, but because it fails to pull. An underdense region works exactly that way. Less mass there means less pull from that direction, and the net effect looks precisely like a push. Half our motion comes from being drawn toward mass. The other half comes from being abandoned by the absence of it. In 2025, a team led by Hans Boehringer at the Max Planck Institute for Extraterrestrial Physics announced the discovery of a superstructure they named Quipu, after the Incan system of counting using knots on cords. Appropriate, since the structure consists of one long filament with multiple side filaments. They mapped it using X-ray galaxy clusters in a survey covering roughly 425 to 800 million light-years, and found Quipu stretching some 1.3 billion light-years, containing the mass of about 200 quadrillion suns, around 200,000 times the mass of the Milky Way. Together with 4 other superstructures the team identified, these 5 contain 45% of the galaxy clusters, 30% of the galaxies, and 25% of the matter in the observable universe, inside 13% of its volume. Boehringer is careful about the record, noting that Quipu is the largest structure in the nearby universe, because larger structures quite probably exist if we inspect ever larger volumes. All of this pulling and pushing produces one measurable number, and we can read it directly off the sky. The faint microwave glow left over from the early universe fills all of space at almost exactly the same temperature everywhere. Almost. Look carefully, and one direction is about 1 part in 800 hotter, the opposite direction correspondingly colder, the signature of our own motion through it. That dipole corresponds to a motion of about 370 kilometers per second from the perspective of the Sun, roughly 230 miles per second, directed, when all contributions are combined, toward the constellations of Crater and Leo. And the local group as a whole moves faster still, around 620 kilometers per second. Sit still for 1 second, and you have traveled further than the distance from London to Cairo. Nothing in the universe is stationary. Not the Earth, not the Sun, not the galaxy, not the local group, not Laniakea. Every one of them is being carried down a gravitational slope toward mass we mostly cannot see, pushed from behind by emptiness, inside a current that has been running since the first structures formed. But here is what those flow maps quietly revealed, once astronomers zoomed out far enough to see the whole picture. The clusters and superclusters stop looking like objects at all. At the largest scale, they dissolve into something else entirely, a pattern that nobody designed and that nobody expected to find. Keep pulling back, far enough that Laniakea itself shrinks to a smudge, and every cluster inside it becomes a single point of light in a map. At that scale, something appears that no one was looking for. On the largest scales, matter is not spread evenly. It is gathered into a network sometimes called the cosmic web, dense clusters of galaxies linked by long filaments and sheets, with large, near-empty voids in the spaces between. Filaments stretching hundreds of millions of light years, meeting at dense knots where clusters sit, with vast hollows between them. Look at a picture of it, and your brain will insist it recognizes the thing. It resembles neural tissue under a microscope. It resembles the inside of a sponge, or the walls between bubbles in a head of foam, or the pattern of cracks in drying mud. And nothing designed it. No process shaped it toward that form. Gravity, working on faint irregularities for 13 billion years, produced a structure that looks unnervingly like biology. But nobody expected any of this. Astronomers went looking for something else entirely. Through the 1980s, teams began building the first genuine 3-dimensional maps of the universe using redshift surveys, measuring how much each galaxy's light has been stretched by cosmic expansion, converting that into a distance, and plotting the result. The expectation was straightforward. Galaxies should be scattered more or less at random, like grains of sand thrown across a floor. Then, in 1989, Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics analyzed redshift measurements of over 15,000 galaxies and found a coherent, wall-like arrangement. The filament they discovered runs about 300 million light-years wide, 15 million light-years thick, and snakes for at least 500 million light-years across the universe. Consider those proportions. 500 million long, 15 million thick, roughly 30 to 1, a sheet, not a blob. Take a bed sheet and hold it up, and you have the shape, if not the scale. And it may be even longer, because it intersects the plane of our own galaxy, where dust blocks the view of its true extent. Structure, where randomness was expected. That single result changed how cosmologists thought about the universe. In 2003, astronomers mapped the Sloan Great Wall, about 1 billion light-years away and 1.4 billion light-years long, almost 3 times the length of the first. Except here the caution begins. In 2011, Researchers suggested that the Sloan Great Wall is a chance alignment of 3 separate structures and not a single structure at all. That is the persistent problem with the very largest claims. We see the sky projected flat, and things that lie at similar distances in the same direction can look connected when they are not. The most extreme claim of all is the Hercules Corona Borealis Great Wall, with a stated major axis of about 10 billion light-years. If real, that would be a structure spanning a substantial fraction of the observable universe. But it has never been confirmed as a physically connected concentration of mass. Hans Boehringer, the astrophysicist who led the Quipu discovery, points out that the Hercules Corona Borealis Great Wall is technically the largest known structure, only with a catch. It has not been confirmed as a single, interconnected thing, which leaves an honest ranking. The largest reliably measured structure is Quipu. The larger claim remains a candidate, an apparent overdensity of gamma-ray bursts on the sky, not a mapped bound object. Scientists hate this kind of ambiguity, and the universe keeps producing it. Now flip the picture, because the filaments are the minority. Voids are the gaps in that structure, and they make up most of the volume of the universe. Analyses of galaxy distributions put that fraction somewhere around 40 to 50%, and by some estimates higher. Pick a point in space at random, genuinely at random, anywhere in the observable universe, and the most likely place you would land is nowhere at all. The most dramatic example sits in the direction of the constellation Boötes, a roughly spherical region around 330 million light-years across, in which almost nothing is found, identified in 1981 by Robert Kirshner, working with Augustus Oehmler, Paul Schechter, and Stephen Schechtman. Its center lies about 700 million light-years from Earth. At normal galaxy density, that volume should contain something like 10,000 galaxies. Surveys since have found about 60 inside it. Now place yourself there and let this land properly. Astronomer Greg Aldering made the point that if the Milky Way sat at the center of the Boötes void, we would not have discovered that other galaxies existed until the 1960s. Think about what that means. Every telescope from Galileo onward would have shown stars and nothing beyond them. No Andromeda smudge on an autumn night. No great debate, because there would be nothing to debate. An entire civilization reaching the space age, convinced that its galaxy was the universe. And being wrong, with no way to know. We can see the cosmic web because of where we happen to sit. That is not a small piece of luck. And here is the honest framing, because the drama around that void is often overstated. Its presence is consistent with the standard model of how cosmic structure grew from small density variations in the early universe, and it requires no exotic explanation. Aldering himself helped show that it is a fairly ordinary void, just an unusually large one. Voids are not holes punched in something. They are what remains when gravity drains a region, matter flowing out along filaments toward the nodes, leaving the middle progressively emptier. You have watched this happen. Rain on a car windscreen. Droplets pull toward each other, merge into rivulets, and the glass between them goes dry. Nothing removed the water from those patches. Gravity simply gathered it somewhere else. The voids are where the matter used to be. But there is a deeper problem, and it strikes at an assumption underneath all of modern cosmology. The standard model rests on the cosmological principle, the idea that at sufficiently large scales, the universe looks broadly the same in every direction and from every location. Local clumps and empty regions are allowed. They are supposed to average out. The often cited scale at which that smoothing should take hold is around 370 megaparsecs, about 1.2 billion light-years. Above that scale, no structure should exist. Then Alexia Lopez started finding them. Working with Roger Clowes at the University of Central Lancashire and Gerard Williger at the University of Louisville, Lopez reported the giant arc from an analysis of quasar light, a structure stretching roughly 3.3 billion light-years, almost 3 times the theoretical limit. Then, at the 243rd meeting of the American Astronomical Society, she reported a second, the Big Ring, 9.2 billion light-years from Earth, with a diameter of about 1.3 billion light-years and a circumference of about 4 billion. If we could step outside and see it directly, the diameter of the big ring would need about 15 full moons to cover it. And then comes the detail that makes this genuinely strange. The big ring and the giant arc sit in the same cosmological neighborhood, seen at the same distance at the same cosmic time, and only 12 degrees apart on the sky. As Lopez put it, we could expect maybe one exceedingly large structure in all our observable universe. Yet here are two huge structures that are even cosmological neighbors. Preempt the obvious objection, because Lopez did. She recognized the risk that her eye was picking up shapes that were not really there, so she ran statistical tests and found the ring unlikely to have formed by accident. Her team concluded that the big ring is real and statistically significant. The proposed explanations remain open. One possibility involves cosmic strings, filamentary defects of great size that could have formed in the early universe. The Nobel laureate Jim Peebles has hypothesized that cosmic strings could play a role in other peculiarities of large-scale galaxy distribution. The alternative is that selection effects and the human tendency to find patterns are producing structures that will not survive larger, deeper surveys. Nobody has settled it. In a 2025 review in Philosophical Transactions of the Royal Society A, Lopez, Clowes and Williger argued that both structures exceed the commonly cited homogeneity scale and, taken together, raise questions about whether the visible universe is as statistically typical as the cosmological principle assumes. If they hold up, one of the foundations under every number in modern cosmology needs revision, which raises the question underneath all of it: how does a universe end up with structure at all? To answer it, we have to go back to the beginning and immediately correct the picture almost everyone carries. The Big Bang was not an explosion in space. It marked the beginning of time, energy, and matter. No debris flew outward into a pre-existing emptiness, because there was no emptiness for it to fly into. Space itself came into being and began expanding everywhere at once. So what came before? Stephen Hawking had the cleanest way of handling that question. Asking what came before the Big Bang, he suggested, is like asking what lies north of the North Pole. The question is grammatically fine and physically empty. Walk north far enough and you simply run out of north. And in the first instance, missions studying the early universe find evidence for a period called cosmic inflation, a fraction of a second in which the universe expanded faster than the speed of light. Here is why that matters for everything we have just looked at. At subatomic scale, the universe is never perfectly smooth. Quantum uncertainty produces tiny, constant fluctuations in energy density, ripples far too small to matter to anything. Inflation took those microscopic ripples and stretched them to cosmic scale. Think of a photograph taken on cheap film, then blown up to the side of a building. The grain that was invisible in the print becomes the dominant feature of the wall. Inflation did that to quantum noise. The faint graininess of nothing became the blueprint for everything. Every filament, every void, every cluster, every galaxy, every star, every planet. All of it traces back to irregularities that were once smaller than an atom. Within minutes, nuclear reactions in the cooling universe produced mass abundances of about 75% hydrogen, about 25% helium, a tiny fraction of deuterium and helium-3, and trace amounts of lithium, with negligible, heavier elements. And this is one of the great quiet triumphs of the whole model. Calculations of fusion rates in the early universe predict that ratio from first principles, and it agrees with the observed chemical composition of the atmospheres of the oldest known stars, which show roughly 75% hydrogen, 25% helium, and less than 1/100% of anything heavier. A prediction made from theory about the first 3 minutes of time, checked against starlight from stars that formed billions of years ago. They match. That is not a small thing. That is a pillar. But for a long stretch afterwards, the universe was opaque. Everything existed as a hot plasma, nuclei and free electrons unbound. Light could not travel in a straight line because photons scattered off free electrons constantly, like headlights in dense fog, bright everywhere and visible nowhere. Then, about 380,000 years after the beginning, primordial protons, neutrons and electrons formed neutral atoms, and photons decoupled, suddenly free to travel unhindered through space, their wavelengths stretched by expansion into a haze of microwave radiation in every direction. That happened when the universe cooled to around 3000 Kelvin, roughly 2,700 degrees Celsius, close to 5,000 degrees Fahrenheit, about half the temperature of the sun's surface today. The fog cleared, all at once, everywhere, and the light released in that instant is still arriving. 2 American spacecraft transformed what we could do with it: the Cosmic Background Explorer, COBE, and the Wilkinson Microwave Anisotropy Probe, WMAP. John Mather of NASA and George Smoot of Lawrence Berkeley National Laboratory shared the 2006 Nobel Prize in Physics for COBE's findings. Then the European Space Agency's Planck mission delivered the most precise image of the cosmic microwave background, imprinted when the universe was only 380,000 years old. That map shows tiny temperature fluctuations corresponding to regions of slightly different densities, the seeds of all future structures, the stars and galaxies of today, millionths of a degree of variation. To feel the delicacy of that measurement, your body temperature fluctuates by more in the time it takes to read this sentence. And from those fluctuations, Planck extracted the inventory of the universe. Normal matter, the stuff of stars, planets and galaxies, contributes just 4.9%. Dark matter occupies 26.8%. Dark energy accounts for 68.3%. Sit with that number for a moment. Everything we have looked at so far, every star in our galaxy, every galaxy in the local group, the Virgo cluster, Laniakea, the filaments, the walls, the ring, all of it is 4.9% of what exists. The remaining 95% is composed of 2 things we have never directly identified. After the fog cleared, the universe went dark again, and stayed dark for a very long time. These cosmic dark ages lasted for 100 million years. Population 3 stars are thought to have begun forming about 100 million years after the Big Bang, from the collapse of pristine gas within dark matter halos, though other work places the end of the dark ages a few hundred million years in, and the timing remains uncertain. For that entire stretch, no star burned anywhere, only cold hydrogen and helium, expanding, cooling, and gravity patiently pulling the faint quantum ripples into denser and denser clumps. An entire universe, holding everything it would ever need, sitting in complete darkness. When the first stars finally ignited, they formed from gas that was about 76% hydrogen and 24% helium, with no heavy elements at all. And because that primordial gas cooled inefficiently, these stars were expected to be far more massive than stars forming today, with simulations suggesting masses from tens to hundreds of times the Sun. The exact scale is still debated. Theorists think they could have been enormous, 100 solar masses or more, and short-lived, flaming out within a few million years. After those brief lives, many died as supernovae and dispersed the first metals into the surrounding gas. Everything heavier than helium, carbon, nitrogen, oxygen, silicon, iron, had to be manufactured inside stars and scattered by their deaths. The universe did not come with those ingredients. It had to make them. Our Sun, born nearly 10 billion years after the Big Bang, shows elemental abundances far higher than the primordial ones. It is not a first-generation star, and almost certainly not a second. The cloud it formed from had already been enriched by earlier stars living and dying, cycle after cycle, each one adding a little more of the heavy material that rocky planets and living bodies require. The calcium in your bones, the iron in your blood, the oxygen filling your lungs right now. Every atom of it was assembled inside a star that died before the Sun existed. The universe needed generations of stellar death to produce something capable of noticing. and it produced structure on every scale to do it, from quantum ripples to filaments to clusters to one warm planet where the chemistry finally became complicated enough to ask questions. But knowing how the web was built tells us nothing about how much of it there is, because when astronomers tried to count the galaxies actually filling those filaments, the answer they got was not just larger than expected, it was so much larger that the number itself is still being argued over. In December of 1995, Robert Williams, then director of the Space Telescope Science Institute, used a significant share of his discretionary Hubble time on an unusual experiment, pointing the telescope at a dark, seemingly empty patch of sky for 10 consecutive days. The decision was contested, and he pushed it through over the objections of senior colleagues. You can understand why. Hubble time was among the most valuable resources in science, and he was proposing to spend 100 hours photographing nothing. The patch sat near the handle of the Big Dipper, chosen precisely because it looked empty. No bright stars, no conspicuous nearby galaxies, nothing anyone had a reason to examine. And that distinction is the whole method. The field was not chosen because it happened to look empty. It was chosen to be empty. Between December 18th and December 28th, Hubble took 342 separate exposures of that one spot. The size of the target is what makes the result land. NASA described the field as roughly the apparent width of a dime seen from 75 feet away, about 1/24 millionth of the entire sky. Hold a grain of sand at arm's length against the night. That is the piece of darkness Hubble stared into. Almost all of the 3,000 objects that appeared in the image are galaxies. 3,000 galaxies in a patch of sky selected for its emptiness. The result was not a fluke, and astronomers went back to check. The Hubble Ultra-Deep Field, collected between September 2003 and January 2004, contains an estimated 10,000 galaxies. In a rectangle 2.4 arc minutes on a side, smaller than a 1 millimeter square of paper held a meter from your eye, and equal to roughly 1/26 millionth of the sky. It includes light from galaxies that existed about 13 billion years ago, some 400 to 800 million years after the beginning. The extreme deep field followed in 2012, pushing deeper still, and a conclusion emerged that changes how you should look at the night sky. There is no empty sky. There is only sky that nobody has watched for long enough. Every dark gap you see between the stars tonight, every patch that looks like pure blackness, is filled with galaxies waiting for a long enough exposure. Which raises the obvious question: how many are there in total? Until recently, the working figure sat around 100 to 200 billion, drawn largely from those deep Hubble observations. Then, in 2016, a team led by Christopher Consolis at the University of Nottingham did something different. They did not tally galaxies one by one. They used galaxy stellar mass functions, descriptions of how many galaxies of each mass exist in a given slice of space, to estimate how many the images were missing. Their paper states it plainly: at least 2 trillion galaxies exist in the currently visible universe, the vast majority of which cannot be observed with present-day technology because they are too faint. A factor of 10 more than astronomers had been working with, and by that estimate, we currently have the capability to see roughly 10% of them. 2 trillion. Try counting them at 1 per second without stopping, and you would need more than 60,000 years. Longer than the entire span of human migration out of Africa. But that number is disputed. In 2021, a team used NASA's New Horizons spacecraft, far enough from the sun to escape the dust glow that brightens the sky near Earth, to measure the cosmic optical background, the summed light of all galaxies. The dust glow matters enormously. Near Earth, sunlight scattering off tiny particles in the inner solar system creates a faint haze called zodiacal light, and it swamps any attempt to measure how dark the universe truly is. New Horizons, out past Pluto, sat above the haze. From there, the sky was about 10 times darker than the darkest view Hubble can manage. Todd Lauer of Noir Lab put the finding directly: take all the light from galaxies Hubble can see, double that number, and that is what we see, but nothing more. Mark Postman was blunter. We simply don't see the light from 2 trillion galaxies. Their argument points toward a total closer to the hundreds of billions than to trillions, except the disagreement is subtler than the headlines made it sound. Consellis responded that the press release and the refereed paper were describing different things, and that Lauer's own paper acknowledged the 2 trillion estimate carries roughly a 35% uncertainty and may yet be compatible with the New Horizons constraint. 2 teams, 2 methods, 1 unresolved number. More sensitive measurements of that background glow from spacecraft far from the dust are what will settle it. And notice what survives the dispute, the underlying lesson rather than the digit. Most of the universe's galaxies, on any of these estimates, are fainter than we can currently observe. Hundreds of billions or trillions. Either way, the overwhelming majority remain invisible. Since 2022, the James Webb Space Telescope has been reaching back into the universe's first few 100 million years and finding things that did not fit. Early galaxies appeared too bright, too massive, too structured for their age. The existence of such early massive galaxies was quickly identified as a possible severe problem. The large masses would be very difficult to explain within lambda CDM, since the amount of matter already converted into stars could exceed the total available in those early halos. That is a hard limit, not a soft one. A galaxy cannot contain more ordinary matter than existed in its neighborhood to begin with. Michael Boylan Colchin laid the problem out in a 2023 Nature Astronomy paper titled Stress Testing Lambda CDM with High Redshift Galaxy Candidates. If the most extreme candidates were real, the standard model itself was in trouble. Since then, the crisis has partly dissolved, though not completely. The high mass interpretation was challenged by models including prominent nebular emission, which could explain the red colors through the contribution of emission lines rather than enormous stellar populations, implying stellar masses smaller by a factor of 10 or more. In plain terms, glowing gas was being mistaken for vast quantities of stars. Then came the strangest population of all. JWST found compact, extremely red objects nicknamed the little red dots, and if all of them were interpreted as massive galaxies, the implied stellar mass densities would exceed the maximum allowed by the total ordinary matter content of the universe. Impossible in the most literal sense, but many of them show broad Balmer emission lines, a signature of an active galactic nucleus. So a more plausible interpretation is heavily obscured black holes rather than impossibly massive galaxies. Newer work from Anna de Graaf's team at the Max Planck Institute for Astronomy, using nearly 60 hours of JWST spectra from 4,500 galaxies, has proposed a further possibility. Supermassive black holes wrapped inside compact shells of gas. Not galaxies at all, in other words. Black holes wearing disguises. The tension has eased, but the number of these objects remains far larger than anyone extrapolated before JWST, even after accounting for obscuration. And some objects have not dissolved under scrutiny. In 2025, Weichen Wang, Sebastiano Cantalupo, and colleagues published a Nature Astronomy paper describing a giant disk galaxy 2 billion years after the Big Bang, discovered serendipitously in a bright quasar field. Nicknamed the Big Wheel, its starry disk stretches more than 100,000 light-years, larger than any other galaxy disk confirmed from that cosmic epoch, and it is some 5 times more massive than the Milky Way. As Cantalupo put it, typically it should have taken the whole age of the universe for a galaxy to grow that large. Our own galaxy needed 13 billion years to reach its present size. This one managed something larger in 2. The explanation may lie in its address. Multi-wavelength observations show it sits in an exceptionally dense environment, where the galaxy number density runs more than 10 times higher than the cosmic average, and mergers are frequent. A node of the cosmic web, feeding one galaxy at a rate the rest of the universe could not match. Which brings us to a fact about the present that rarely gets said out loud. Observations indicate that star formation activity peaked about 10 billion years ago and has since dropped by roughly a factor of 10. Astronomers call that peak cosmic noon. We live long after it. Radio measurements of atomic hydrogen in distant star-forming galaxies found that massive galaxies have gas reservoirs able to sustain their current star formation for only about 900 million years, unless fresh gas keeps flowing in. Cold gas is the fuel. Once it is used up, or heated, or blown out, the manufacturing stops. The universe is not dying, but it is quietly aging, burning through its remaining fuel, forming fewer stars each billion years, settling slowly toward a redder, dimmer version of itself. Everything we have looked at exists in the long afternoon, and all of this, every galaxy counted, everyone still hidden, accounts for a small fraction of what actually holds the universe together. In 1933, the Swiss astronomer Fritz Zwicky studied the Coma cluster, roughly 1,000 galaxies strong. The cluster moved so fast it ought to have burst apart, and did not. He calculated that it must be hundreds of times denser than its visible glowing matter alone suggested, meaning some kind of invisible material, which he called dunkel Materie. Dark matter must be binding it. The numbers were stark. Zwicky measured galaxy velocities averaging around 1,000 kilometers per second, about 600 miles per second, where the visible mass predicted only about 80. Picture a fairground carousel spinning 10 times faster than its bolts should allow, with nobody flying off. Either the bolts are stronger than they look, or something is holding the riders down that you cannot see. The concept did not catch on. As Princeton astrophysicist Nita Barkall has put it, it was too outrageous to believe for almost 4 decades. Then, in the 1970s, Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies, how fast stars orbit as a function of their distance from the center. The Newtonian expectation is one you can check in our own solar system. Mercury races around the Sun in 88 days. Neptune, far out, crawls. The further you sit from the mass, the slower you go. Galaxies should behave the same way, with orbital speeds declining outward from the dense center. Instead, the velocities stay roughly constant beyond a certain distance. Rubin's most influential paper, in the June 1980 issue of the Astrophysical Journal, charted 21 spiral galaxies across a range of sizes and luminosities. All of them had flat rotation curves extending far from their centers. Not one exception. Whatever was happening, it was happening everywhere. Independent confirmations arrived from gravitational lensing, from the microwave background, and from the growth of large-scale structure. But the cleanest single piece of evidence came from a wreck. In the Bullet cluster, 2 galaxy clusters collided. Chandra's X-ray imaging shows the hot gas, which accounts for most of the ordinary visible matter, piled up in the middle, slowed by the impact. The gravitational field mapped through lensing sits somewhere else entirely. The mass and the visible matter separated. The gas collided and stopped. Whatever holds most of the mass sailed straight through, because it barely interacts with anything, including itself. But the case is not closed, and the honest version includes the other side. Modified Newtonian dynamics, proposed in the 1980s, suggest that Newton's second law should be modified in the limit of very small accelerations. The theory is genuinely successful at explaining the rotation curves of galaxies. Impressively so, often with fewer free parameters than dark matter models require for the same galaxies. Its difficulty comes at larger scales. As the current position stands, none of the proposed modified gravity theories can describe every piece of observational evidence at the same time, suggesting that even if gravity has to be modified, some form of dark matter would still be required. No modified gravity model reproduces the bullet cluster separation and the microwave background's detailed structure simultaneously, and yet the particle has never been found. Direct detection experiments have pushed their limits down by orders of magnitude and reported null results across the standard mass range. As of late 2025, The LZ experiment had entered what physicists call the neutrino fog, the point where an irreducible background of neutrinos begins to mimic the signal they are hunting. Decades of searching, increasingly sensitive detectors, nothing. We have overwhelming gravitational evidence for something we cannot catch. In the 1990s, two rival teams set out to measure how fast cosmic expansion was slowing down. Saul Perlmutter led the supernova cosmology project, begun in 1988. Brian Schmidt formed the High-Z supernova search team in 1994, with Adam Rees leading the analysis of its data. Both assumed deceleration. Gravity pulls, expansion should be losing steam. Instead, the most distant supernovae came back dimmer than they should have been. The only plausible explanation was that expansion is speeding up. The first results, 10 supernovae from Schmidt's team, 42 from Perlmutter's, were published in 1998 and 1999. All three shared the 2011 Nobel Prize in Physics. Nobody predicted it, and the cause, whatever drives it, got the name dark energy. For 25 years, the simplest assumption held: dark energy is constant, a fixed property of space itself. Then the Dark Energy Spectroscopic Instrument reported that when its measurements are paired with a microwave background, weak lensing, and supernovae, mounting indications suggest the impact of dark energy may be weakening over time. The 2025 DESI data release found that including supernovae, the preference for evolving dark energy over the standard model ranges from 2.8 to 4.2 sigma, depending on which supernova sample is used. That has not reached 5 sigma, the gold standard in physics, and a 3 sigma result has about a 0.3% chance of being a statistical fluke, while many 3 sigma results in physics have faded away with more data. The analysis hid its results from the scientists until the end to guard against unconscious bias. Will Percival, co-spokesperson for DESI, framed it carefully. It is looking more and more like the standard model may need modifying to make these datasets agree, and evolving dark energy seems promising. Consider what hangs on that. If dark energy is constant, the universe's future is settled, accelerating forever, everything drifting apart on a schedule we can already write down. If dark energy weakens or strengthens or reverses, the long-term fate of everything becomes genuinely open again. We do not know how this ends, and admitting that is more honest than any confident answer. But whichever version is true, the acceleration is already happening, and it is doing something to the universe we have spent all this time measuring. Piece by piece, it is taking it away. The mechanism is simple, and once you see it, it is difficult to unsee. If expansion accelerates, then beyond a certain distance every galaxy is receding from us faster than light, which sounds like a violation of the one rule the universe supposedly never breaks. So deal with that objection first. Nothing is moving through space faster than light. The expansion of space can separate two objects at an apparent speed greater than light without violating relativity, because it is not the object moving through space faster than light. Space itself is stretching between them. Relativity governs motion through space. It sets no speed limit on the stretching of space itself. So how do we see those galaxies at all? Only because their light left long ago, when they were far closer to us. That ancient light is still arriving, still in transit, still crossing a gap that was much smaller when the journey began. But light those galaxies emit today will never reach us. The distance between us grows faster than light can close it. Those photons will travel forever and fall further behind. And this is happening now, continuously, to galaxies at the edge of what we can see. As a galaxy approaches the cosmic horizon, its light stretches to longer and longer wavelengths, redder, then infrared, then microwave, then nothing our instruments can register. Its apparent brightness collapses. Its clock, as we see it, slows. Nothing explodes. Nothing snaps shut. The galaxy simply fades, reddens, dims, and stops delivering information. like a ship crossing a horizon at sea, except the water beneath it is being unrolled faster than the ship can sail back. One by one they are leaving, permanently, which leads somewhere genuinely unsettling. In 2007, Lawrence Krauss and Robert Scherer published a paper demonstrating that as the current model is extrapolated forward in time, all evidence of the Hubble expansion will disappear, so that observers in our island universe will be fundamentally incapable of determining the true nature of the universe, including the existence of the highly dominant vacuum energy, the existence of the cosmic microwave background, and the primordial origin of the light elements. With those pillars of the Big Bang gone, they argued that epoch will mark the end of cosmology and the return of a static universe. Roughly 100 billion years from now, the exact figure depends on the model. The only thing left within reach will be the merged remains of our own local group. Set that against the present. The universe is 13.8 billion years old. That future sits 7 times further into the future than the entire past. And as Krauss and Scherer put it, for all intents and purposes, the universe will appear static, and all the evidence that now forms the basis of our current understanding of cosmology will have disappeared. Picture yourself as one of them. You stand on a rocky world orbiting a red dwarf inside a single enormous elliptical galaxy. You have a superb telescope, better than anything we have ever built. You point it into the dark beyond your galaxy's edge, and you find absolutely nothing. No other galaxies, no faint microwave glow filling the sky. You do the measurements carefully, you publish, and you conclude, correctly by every piece of evidence available to you, that you inhabit a static island universe surrounded by empty space. No error, no sloppiness, every observation sound, every calculation right, and the conclusion profoundly, irretrievably wrong. That is what makes this the strangest fact in the whole story. We exist inside a narrow window, late enough that stars have burned for billions of years, forged the heavy elements, built rocky planets and observers capable of asking, early enough that the evidence has not yet been erased. The cosmic microwave background is still detectable, distant galaxies still shine, the expansion is still measurable. None of that will be true forever. The record is still readable, and we happen to be reading it. Consider what that means for how we treat the evidence we do have. Somewhere in the future, an intelligent species will look at an empty sky and draw an honest conclusion from complete data, and be wrong, which is a reason to hold our own conclusions carefully. But this era has also handed us something new, a way of receiving information that does not depend on light at all. On September 14, 2015, at 51 minutes past 5 in the morning Eastern Time, both of the twin LIGO detectors in Livingston, Louisiana and Hanford, Washington, registered a gravitational wave. Analysis showed 2 black holes, about 29 and 36 times the mass of the Sun, merging 1.3 billion light-years away. They formed a black hole of around 62 solar masses, radiating energy equivalent to 3 suns in a few tenths of a second, making the event, for that brief moment, the most powerful radiant object in the universe. Gravitational waves were emitted with a power 10 times greater than the light of every star in the observable universe combined. And nobody saw a thing. That colossal event released almost nothing as light. What reached Earth was a ripple in the geometry of space itself. And here is the measurement that makes the detection almost unbelievable. The LIGO mirrors moved by roughly 1,000th the diameter of a proton, equivalent to measuring the distance to Proxima Centauri, 4¼ light-years away, to within the width of a human hair. The result led to the 2017 Nobel Prize in Physics for Rainer Weiss, Barry Barish and Kip Thorne. Then came the event that connected the new messenger to the old one. On the 17th of August, 2017, 2 neutron stars in the galaxy NGC 4993, about 130 million light-years away, completed a spiral inward that had taken millions of years, and ended in a collision lasting fractions of a second. The Fermi gamma-ray burst monitor independently detected a gamma-ray burst about 1.7 seconds after the merger time. Within hours, telescopes worldwide had identified the afterglow across the electromagnetic spectrum, from gamma rays to radio. What they saw was a kilonova, an event predicted more than 30 years earlier and never before confirmed, with radioactive heavy elements streaming outward at a fifth of the speed of light, the colour shifting from very blue to very red over the following days, faster than any stellar explosion ever recorded. These mergers disperse heavy elements such as gold and platinum throughout the universe. Analysis of the event put the ejected heavy material at roughly 6% of a solar mass, around 20,000 Earth masses of matter, including about 200 Earth masses of gold. Now make it personal. Every gold atom on Earth, in every ring, every coin, every contact inside the device you are holding, was forged in a collision like that one in a galaxy far from here before the Sun existed. Those atoms drifted through interstellar space, joined the cloud that collapsed into our solar system, and settled into the crust of a planet that had not yet formed. You can wear something older than the Sun, and gravitational waves matter for another reason. Light can be absorbed or scattered by matter along its path. Gravitational waves pass through everything almost unimpeded. Dust blocked our view of our own galaxy for centuries. It cannot block this. Which brings us back to the question underneath everything. Current observational constraints favour a spatial geometry that is nearly flat, with about a 0.4% margin of error. Flat, in this context, has a precise meaning. Draw an enormous triangle across the cosmos, and its angles add to 180 degrees. Parallel beams of light stay parallel forever. Space does not curve back on itself like the surface of a sphere. And here is where people leap to the wrong conclusion. Flatness constrains the geometry. It says almost nothing about the total size. A flat universe could be infinite, but space can also be finite without an edge, or multi-connected, and if it widely encompasses the observable region, no signature of its finiteness will ever show in the data. Astronomers have looked for that signature directly, searching the microwave sky for matched circles, the repeated patterns you would see if light had wrapped around a finite space. Planck's analysis excluded, at 99% confidence, any topology predicting matched back-to-back circles above a certain size, placing the lower bound on the size of the fundamental domain at roughly the radius of the last scattering surface itself, which is an honest limit rather than an answer. The method cannot see past the edge of what we can see. Other work by Mihran Vardanyan, Roberto Trotta and Joseph Silk used Bayesian model averaging across cosmological datasets to place the curvature radius above 42 gigaparsecs at 99% confidence, corresponding to a lower limit of at least 251 Hubble volumes, at least 250 times the volume of everything we can observe. And that is a floor, not a ceiling. The same group found that given current data, the probability that the universe is spatially infinite lies somewhere between 67 and 98%, depending on the choice of priors. Notice what that sentence actually is. Not a measurement, a statement about models and assumptions. Physicists remain genuinely split on whether infinite is even a physically meaningful claim, or a placeholder for larger than anything we can test. Running through all of it is a single working assumption, that we occupy no special position unless evidence forces us to conclude otherwise. Copernicus moved the Earth from the centre. Shapley moved the Sun out of the centre of the galaxy. Hubble removed the centre entirely. Every time we assumed we were somewhere important, we were wrong. But the principle has a genuine limit, and honesty requires stating it. We cannot exist at a random moment in cosmic history. Observers made of carbon and oxygen and iron require a universe that has already run generations of stars. Our position in space may be unremarkable. Our position in time cannot be. Not central, but not randomly sampled either. And the Standard Model still has trouble close to home. The dwarf galaxies orbiting the Milky Way do not appear randomly scattered. Many of them sit in a thin, rotating plane, which is not what simulations of dark matter structure formation naturally produce. Astronomers call it the plane of satellites problem, and it sits alongside long-running disputes over how many small satellite galaxies our galaxy should have. Some recent analyses argue the tension has dissolved once selection effects and simulation details are handled properly. Others maintain the problem is real, and as one review notes, the coming facilities should turn into dwarf galaxy discovery machines, letting us trace and characterize these structures throughout the local group, while cautioning that as we dig deeper into our local patch of the universe, the planes of satellites problem is unlikely to be the only riddle needing to be puzzled out, unresolved, testable, being tested right now. One more thing sits inside all this scale, and it does not resolve. Somewhere between hundreds of billions and 2 trillion galaxies, trillions upon trillions of planets, and not one confirmed signal from anybody. Scale does not solve that problem. Scale sharpens it, because every galaxy added to the count makes the silence louder rather than quieter. We do not know what the silence means. We may simply not have listened long enough, in the right way, which, as the deep fields taught us, has been the answer more than once. The Vera Rubin Observatory began its 10-year survey in June of 2026, sweeping roughly 18,000 square degrees of sky repeatedly. The European Space Agency's Euclid is already delivering space resolution imaging across thousands of square degrees, and NASA's Nancy Grace Roman Space Telescope goes deeper over a smaller area. Combined public investment across the three exceeds $6 billion, and by 2027 all three will be covering much of the same sky at once. Here is the pattern worth holding on to. Every generation of instruments has enlarged the universe. Galileo turned a band of light into stars. Herschel's counts became a galaxy. Hubble's Cepheids turned nebulae into island universes. The deep fields turned emptiness into thousands of galaxies. Not once has a better telescope made the universe smaller. So take the whole climb, one rung at a time. Our galaxy's glowing disk, 100,000 light-years. The dark halo enclosing it, by some estimates approaching 2 million light-years across, perhaps 20 times wider than the light. The local group, 10 million light-years, 100 times our galaxy. The Virgo supercluster, 110 million, more than 1,000 times. Laniakea, 500 million, 5,000 times. And the observable universe, 93 billion light-years, about 930,000 times, the width of the Milky Way. Stated plainly, our galaxy is roughly 1/millionth the width of everything we can see, and what we can see is only the portion whose light has had time to arrive. Go back outside. That faint band of light still runs from horizon to horizon, exactly as it did before any of this was known. Nothing about it has changed. Everything about what it means has. At the beginning, the difficulty was that we were inside the thing we were trying to see, trapped in a disk, peering through dust, unable to step back far enough to view our own galaxy whole. We are still inside, but the walls are no longer made of dust. They are made of time, a sphere drawn not by any physical boundary, but by how far light has managed to travel since the beginning. And we are inside a moment too, late enough to have stars and chemistry and eyes, early enough that the evidence has not yet drifted beyond reach. You are standing on one rocky planet, 26,000 light-years from the center of one barred spiral galaxy, inside a family of 100, on the outskirts of a supercluster, near the rim of a flow of galaxies falling toward mass we cannot see, in one of perhaps 2 trillion galaxies, in a universe that almost certainly continues far past our sight. And after 13.8 billion years of expansion, collapse, ignition, explosion, and enrichment, this universe assembled matter capable of measuring itself. That is what you are. That is what this was for. One number is what tonight was really about. Our galaxy is roughly 1/millionth the width of everything we can see. It sounds like a verdict on your size. It isn't, because that number does not exist out there, Not in the filaments, not in the voids, not in a single one of 2 trillion galaxies. Nowhere in 93 billion light-years is there anything capable of holding it, except a few pounds of warm matter behind a pair of eyes. And tonight, one of the places in this universe where that number exists is you, in a dark room, awake, somewhere on a rocky planet, 26,000 light-years from a galactic center. Size is measured outward. Meaning gets measured inward. The universe is not larger than you in the way you are afraid of. It is larger than you the way the ocean is larger than someone who can swim. Thank you for staying with me through all of it, the whole long climb. If this journey meant something to you, a like and a subscribe are how you tell me. There is far more of this universe still waiting, and more journeys are coming. Quieter ones, stranger ones. I hope you'll be here. Sleep well tonight. The band of light is still overhead.